Okay, so as a tool, we need a network flow algorithm. And I first want to explain what a network flow is. So we need a graph that's defined in terms of its vertices and edges. And I want each edge to have a different capacity. So I'm calling it a capacitated directed graph. Capacitated means that for every edge has some maximum capacity. You can really think of these as tubes through which water is flowing. And I'm calling this capacity for edge ij, I'm calling it Cij. This is a mapping from the set of edges to the set of non-negative real numbers. And through each edge we can have a flow. Fij, which is also a mapping from the set of edges to the set of non-negative real numbers. And this flow has to satisfy a number of constraints. So we have a special node S, the source. And another node which is the sink. And because I want to distinguish S and S from each other, this is often called T for target. And now in between I can have a couple of vertices. I'm giving them numbers. Let's say this is 1, 2, 3, 4. And then I have these edges specified by my set E with capacities, so CS1 for this edge, CS2 for that edge, let's say this is C13, C23, C24, C3T, and C4T. And I've just picked some random graph here. Now for this flow we have a couple of constraints. So the flow on an edge ij cannot be larger than the capacity on this edge. So as a constraint, this is called the capacitation constraint. And we need a conservation of flow. So if we look at a single node, then the sum of the incoming flows has to equal the sum of the outgoing flows. So the incoming flows are sum over I, Fij. Those are the flows that go into a node J, and then the ones that go out from J to any other node K. This is the total amount of outgoing flow, and this is the conservation constraint. And I could say this is for all pairs of edges in E, or I could simply say this is for all vertices where I assume that an edge that I did not indicate in this sparse graph, like this one here, simply has a capacity of 0. And if I use that convention, I can just say for all I, j, k in the set of vertices. And the total flow, due to the conservation of flow, I can measure it anywhere through any complete cut, but it's especially simple near the source or near the sink. So for example, I can measure how much flow is going from the sink into any other node and sum over all of these. That gives me the total flow. So S again is the source node. So there's your flow problem. And I want to show, in terms of slides prepared by Kevin Wayne, how this whole thing works. Shown here is the Ford-Fulkerson algorithm. Ford-Fulkerson or augmenting path algorithm. So we have a source, we have a sink, and we have given through some higher power this directed graph G, where the capacities are indicated in black, and initially we have no flow whatsoever. And the aim of this algorithm is to find the maximum flow through this graph. This is of interest because the max flow min-cut theorem tells us that the maximum flow can also be used to find the minimum cut in a graph, and the minimum cut is what we need to optimize this binary MRF. So we start by finding some path from source to sink, like this one here. And along this path, we have the capacities 10, 8, and 10, so the bottleneck is 8. So I can send up to 8 units through this path. And on the top, you now see that where we previously had a flow of 0, because the flows are indicated here in blue, we now have a flow of 8, 8, and 8. And we can now update the residual capacity. So when I've sent a flow of 8 pointing in this direction, which had a maximum capacity of 8, then I can clearly no longer send. However, in principle, I can send some virtual flow in the other unit, namely up to 8 units, because I sent 8 units this way. So by just sending, let's say, 6 units rather than 8, I would virtually send 2 units in the opposite direction. Okay, so this is the kind of computation that's now going to happen. Whereas here, let's look at this edge here. If we send a flow of 8 through a possible capacity of 10 in this direction, it means we still have a flow, or we still have 2 spots free to send more in this direction, but I could also send up to 8 units in the opposite direction by just sending less in the forward direction. Okay, this is the computation that you now see on the bottom. This is the so-called residual graph down here. The residual capacities. And you see what I just showed. So now we have still 2 slots left to send flow in this direction, but up to 8 slots to send something in the opposite direction. If you look at this edge, this was previously pointing, the edge here in the middle, it was previously pointing in that direction with up to 8 units. And now we are in the residual graph, we can only send up to 8 units in the opposite direction because we've completely exhausted the forward direction. We've saturated this edge, but we can send, at least virtually, something in the opposite direction now. And we pushed 8 units of flow, so my current flow value is 8. Now I substitute the original graph with this residual graph, and I can now search for any augmenting path. So one augmenting path, for example, would be, we could take a direct direction here, or we could take this path. Let's see which one Kevin Wayne took. Okay, this is also a path which permitted us to still send flow in the forward direction. If you look at the current bottleneck, it is 2. So we're going to update the complete value of the flow, which is now 10. And we're also going to update the residual graph, which has happened at the top, and the flow value is now 10. Now we keep playing this game. So we find so-called augmenting paths that allow us to push more flow from source to sink until at last our residual graph has no more, until there is no viable path left. So let's look at this situation now. Current flow value is 16. We start at the source. I cannot send something in either this direction or I cannot send something along the top arrow here because I have a capacity of 10, but only in this direction. I have 0 capacity in the forward direction. However, I could send up to 4 units in this direction, and then I could send something in this direction, and something in that direction, something in that direction. Or another augmenting path would be to continue here, and then I cannot continue here, I cannot continue there, but I can take a turn and go on. Okay, so Kevin Wayne took one of these possibilities and updates the residual graph and finds the current flow, which is 18. And now we have just a single augmenting path left. So I can travel in this direction. And then here I must necessarily turn this way. Then I can continue here and down there. And the bottleneck here is 1. So I'm going to increase my flow from 18 to 19. And then I think we're done. So flow is 19. And at this point, we no longer find any augmenting path. Okay, so from S to node number 2 does not work. Here I could send 1 unit of flow to node number 3, but from 3 onwards, this is a dead end. I cannot send anything further. So I have found the maximum possible flow, which has a value of 19. And furthermore, we have at the same time obtained a cut, namely in terms of all the nodes that in the residual graph, let's go back to the residual graph, in terms of all the nodes that can be reached from the source or from the sink. So you see that I have a forward edge from the source to this node number 3, which brings it into the cluster belonging to the source. And from the sink, I have forward nodes to this one and to that one and also to that one, which brings all of these nodes into the cluster belonging to the sink. I did not understand. I really go by the residual graph. And it's enough, I think your argument is right, it's enough to just look at what can be reached from the source, and then the rest follows from this. Okay, so
couldn't there be nodes which are completely cut off because all channels are filled? So which neither
yes, and for these there is ambiguity where exactly my cut goes through, and I could assign them to either source or sink. You're right. For such degenerate cases. And we found a flow value of 19. On the top is the original graph, where again in black are the capacities and in red are or in blue is the flow that was pushed. And to compute this flow, we're only looking at the outgoing edges. So here, for example, we had outgoing flow 9 in this direction and an outgoing flow of 10 in that direction. And well, here the flow happens to be 0, but more importantly, this edge is pointing in the wrong direction. So we're not counting this. We're only counting the flow that's going away from the source. And the flow here is 19. And if we, instead of the flow, if we count the capacity of all the edges that go out from the source cluster, we also have 19. And this is always the case. This is the max flow min cut theorem, which tells us that the maximum flow that can be, or the value of the maximum flow corresponds to the cheapest cut that can be found anywhere in the graph. So by cut, I mean anything that separates source from sink. And if, for example, I would cut here, the capacities would be 4 plus 8, which is 12, plus 19, which is 21. But the minimum cut is only 19. Okay, so you won't find any cut that is cheaper than this one. You might find one, like you mentioned, that has the same value. So the max flow problem is to maximize all elements of this flow vector to obtain the greatest possible overall flow subject to all these constraints, the capacitation constraint, and I think I didn't mention non-negativity before. So every flow can be 0 or larger than 0. This is for all pairs of edges in the edge set. And then we have the flow conservation. Which holds at all nodes except for the source and sink. So this was the max flow problem, and this is solved by, there are many algorithms nowadays, but one of the most fundamental ones is the Ford-Fulkerson algorithm. In Ford-Fulkerson, they look for any augmenting path. There are also heuristics to find better paths. There is, for example, I'm not sure now, is it Edmond Carp or Edward Carp? Sorry, Tom? Yeah, which looks for the shortest augmenting path. So this here looks for any augmenting path iteratively. This Edmond Carp looks for the shortest augmenting path. And there are many other algorithms that have somewhat better computational complexity. But even so, this is a polynomial time algorithm, so it's I don't know what it is exactly, but it's in any case polynomial complexity. Now I mentioned this theorem, which says that the maximum flow that can be pushed through a graph is always equal to the minimum capacity, and I will define what a minimum capacity cut in a moment. So the maximum value of a source sink flow is equal to the minimum capacity over all ST cuts. This is an important theorem. So what is a cut and what is a minimum cut? So so let's define this. An ST cut, you write script C, consists of two sets, script S and script T, which partition the original set of vertices. And it's a disjoint partition, so the intersection of S and T is the empty set. And it's called an ST cut because it is a partition such that the source is part of the set S and the sink is part of the set T. The cut set of C is the set of all edges going from S to T, but not the other way around. So it's the set of edges ij where I is in the set S and j is in the set T. But not the other way around. So in particular for a cut, we count all the flow, or we count the capacity, or we look at only the edges that are outgoing, but not at the ones that are incoming, when my source node S is somewhere in this set, capital S. So this is the cut set, and then such a cut set has a capacity. The capacity of the cut over the edge capacities the cut set. Or another way to write this is Ij must come from this Cartesian product of set S times set T. And this allows us to define another problem, namely the min-cut problem. Let me call this here C of S and T. The problem is to minimize the cost of a cut over the sets S and T. And this min-cut problem is easy to write down in this form, but it's much harder to express it, well, not extremely hard, but it's harder to express it in terms of the original variables. You have to, so one formulation is to introduce or to look at all possible paths from source to sink. So you can formulate this using dual variables, and one way is to introduce a potential for each node, putting the source at potential 0 and the sink to potential 1, and then assigning each intermediate vertex some potential value such that the differences between potentials reflect the capacities, and the cost of the cut can then be measured by the total potential difference across the cut set. Okay, so if you have directed graph from somewhere, then the augmenting path algorithm can be used to find the maximum flow, or I have not given the proof for this theorem, or the value of the minimum cut. And this theorem is important in this context because one of the two problems is much easier to formulate than the other one.